Okay. So today,
Should we record?
huh?
Recording?
It's already on.
Oh.
I did it. I'm multitasking. I just enter, put the notes, press recording, almost perfect. So one question, and try not to lie, okay? Just say the truth. Did you try to do the exercise I suggest? Huh?
Yes, but not the last one. The last one.
Okay, no, but okay, but were too difficult? You did not try, so you don't know.
Yes.
So you cannot, you should not try. You should shut up. You tell me when you tried. Okay? No, but I'm joking. Did you try and not succeed, or you did not
No,
try?
I wasn't.
Okay, so you don't know. For those who tried, were the exercises difficult or very difficult?
For me, it's difficult.
I forgot what was the last one?
It's about the ensemble. Starting from the harmonic oscillator down the state. I wasn't sure what I'm supposed to do. Then the mathematical.
No, but what was the question? I really don't remember.
To write the density matrix.
Or what?
Of a harmonic oscillator in the ground state.
Yes. So, what is not clear?
I don't know where to start from.
Okay. Does anybody...
Except that I also did.
Shut up. Not shut up. Shout. Shout.
I didn't do that too. I did.
Sorry, it's not shut up. I want to say shout.
I did another one, but I didn't. I
Okay.
couldn't do that one.
Yeah, this is recorded, so people will think that I'm an awful person saying. Okay. Now, so I'll give you a suggestion, okay? So that you try. If I tell you I want to write down a density matrix. So you have two states, psi 0 and psi 1, whatever, okay? I tell you, I would like to write down a density matrix such that the system has probability P0 to be psi 0 and probability P1 to be psi 1. What should I write? No, I'm just calling psi 0, psi 1. It's not that it's two states. Okay?
P1
So I have
projection.
1, but the projection operator of 1 plus 0.
Okay.
Projection
So with probability P0 should be in psi 0. With probability P1 okay? So I'm not considering that this is a two-state system. I'm just saying that whatever the system is, only two terms enter. Okay, to simplify, to make it simple. Okay, then I have another question. If you have rho, okay? So, rho is an operator, right? So how do you write rho in the coordinate representation?
Bracket will be
So it should be x prime, right? So this is the matrix element of the operator rho in the coordinate representation, right? Is it okay? For you, I'm talking to you.
yes.
Okay. Is it okay over there? Okay. So I would like to write down this row. This is just a notation, okay? So I would like to write this x rho x prime. So what should I write? Tell me.
E0,
Hmm?
absolute value of psi 0 x,
X.
psi 0.
Okay. What? Okay. Plus
The same for psi 0.
okay. Huh? Now, what is x plus psi 0?
Psi 0 x.
So it's the
Wave
wave function. Okay. So this is nothing else. So now you see that now I'm writing the matrix element. So this is an operator. This is a matrix element. So this is a complex number. Okay. So this is equal to P0 psi of x psi 0 of x psi 0 of x prime. Plus P1 psi 1 of x psi 1 star of x prime. Right? Okay. Now, in the case if I would like, so what was the question?
I have to write the harmonic oscillator. The density matrix of the harmonic oscillator in the ground state.
Okay, in the ground state. So this means that if psi 0 is the ground state, so if I just say I want to write down the density matrix in the ground state, this means that, for instance, in this case, P0 should be 1 and P1 should be 0. But now, do you know the wave function of the harmonic oscillator in the ground state? Do you know it? It's e to the minus x squared, okay, divided by something. So this will look like e to the, apart from normalization, e to the minus x squared plus x prime squared, with in units of the appropriate length. Okay? Is it clear now? Is it clear now?
Yes.
Very good. Okay. So today we start a new chapter. Okay, we will do more exercises. I know that Giuseppe Santoro told me that you did some exercises on two-level systems today, right? So today we start discussing perturbation theory. Okay? So, perturbation theory refers to some theoretical approach which allows you to compute. I mean, perturbation theory applies to an infinite number of different models, okay? And the idea is the following in general. Suppose that you have a given problem that you don't know how to solve. And suppose that there is a model whose solution is something you know. Okay? Now, sometimes it is easy to develop a perturbative approach, meaning that there is a scheme such that starting from the solutions that you know, then you can construct a solution for the unknown problem, okay? If somehow the unknown problem is not far away from the known one. What we are, I mean, and the idea is very general, okay? What we are going to do is to see how this idea applies to the problem of determining the eigenvalues and eigenfunction of, for the moment we will discuss a time-independent Hamiltonian. Okay? Is the problem clear? So, for example, so before starting the example, so how many problems you know how to solve for a quantum system, such that you know how to compute the eigenvalue and eigenstates? Yeah, harmonic oscillator.
Hydrogen atom.
Which is already pretty difficult, huh? You know, somebody, okay. Then?
Particle in a well, particles.
So all these rectangular potentials, what it is, something, you know? But there is, I mean, there are other solutions, okay? Other cases which people may, for which exact solutions are known. Huh? But of course, in many cases, exact solutions are not known. But then you want to find a way to study, okay? So, suppose that you have, for instance, suppose this is an harmonic oscillator, okay? Now, imagine that for some reason you are not, I mean, your system is not confined in an harmonic oscillator, but it is confined in an oscillator in which there is a very small bump. Okay? Here. It's not really important. I mean, suppose that there is a bump, or you can imagine that it goes like this. Huh? Just a tiny deformation. Now, do you know how to compute the eigenstate and eigenvalues? This is easy to answer. No, you don't know. Okay? So I'm pretty sure, you are pretty sure, you can relax. You don't know how to compute them. Right? But then what you want to really to find a way in which you can get some ideas about the system. Now it is clear that we have to define what does it mean tiny. Okay? If this is a tiny perturbation, and again I stress, I would like to understand tiny by itself does not mean anything. So if there is a very tiny perturbation, then probably the wave function will not that different from the harmonic oscillators. The harmonic oscillator, okay? There will be some difference. But the smaller is the perturbation, the smaller is the difference between the exact wave function and the harmonic oscillator wave function. Okay? So, the idea is the following. You know the full solution for the harmonic oscillator, you really want to construct the true solution for the oscillator with a bump, okay, in such a way that you have kind of an iterative procedure. That the more terms you put, the closer you are to the exact solution. But the good thing would be that if there is only a tiny deformation, then you need to add only a few terms. Because of course, if you have to add an infinite number of terms, it does not make sense. It is the same as just solving the exact problem, that we don't know how to do it. Okay? Good. So you see the idea of perturbation is not only valid in quantum mechanics, okay? The same is true, for instance, if you have just a ball somewhere and you want to study trajectories of the motion of a classical soccer ball, and you know how to study the problem in a given potential, and then you do a small deformation. Then probably the trajectory will be slightly deformed, okay? So there are many, many different ways, okay? So just there is an idea based on perturbation that you really want to construct the solution of something, some problem that you don't know how to solve, starting from a point in which the solution is known. But this requires a kind of an idea of continuity, okay? So if a solution is known in one point, you just modify a little bit parameters, then the solution will be not much different from the exact solution, okay? So there are several. So again, so what we want to do is just do perturbation theory at the level of determine solution of the Schrödinger equation. So today we are going to study time-independent problems. Okay? So the first thing we want to study is time So the Hamiltonian is time independent, okay? Now, within these time independent problems, it is important to distinguish two cases. The case in which the spectrum is non-degenerate, okay? And the case in which there is some levels which are degenerate. Okay? So we have to consider two separate cases. Right? So today we'll consider the non-degenerate case. Okay? Now, since we have a time-independent Hamiltonian, the goal is to compute the eigenvalues and the eigenfunctions. From there, you can study any strange dynamics. Okay? So the problems can be set in this way. So I have a system which is governed by an Hamiltonian, H, which is given by H0 plus lambda V. This is not something we know how to solve. But what we know is how to solve H0. So H0 is a case that we know how to solve and has a set of eigenstates which are called phi 0 n, and eigenvalue is 0 n. Okay, I assume that I know how to solve this, to determine all this exactly. What I would like to know is to determine the solution of the full problem, lambda v. I just follow this denotation so that when I send you the notes, this is what I want to determine. So I want to determine phi n of lambda. So now, for the full problem, both the wave functions, so the eigenstates and eigenvalues, they will depend on lambda. Okay? Now, I will consider case in which the spectrum is non-degenerate for the moment. So you should ask me why.
Why?
You will see the mathematics, okay? But I would like to just convey some intuition. But then you tell me if it's intuition or it's just confusion, okay? So, when you do perturbation theory, as I told you, essentially you want to have some continuity between the deformed solution and the exact solution. So when this lambda goes to 0, this solution goes to this. Okay? So this means that, for instance, if I would plot the eigenvalues as a function of lambda, then, for instance, I just pick up a given one, okay? Then I should expect that, say, suppose this is E3. Then I will have something, okay? So if I go, okay, so I have E4, this is E4, and I have something else. This is just an invention, okay? Now, perturbation theory, as I said, works and up to the point in which I can make connection between, the perturbed solution and the unperturbed solution. Now you see that if lambda becomes too big, that there is something which happened here, okay? Then, for instance, if just imagine that something else like this happens, then you cannot say that this comes from E3 or this comes E4. Okay? So if lambda becomes too big, then probably this approach is not good. Now you want to stay here, close to this region. But there is one subtle situation that you already know. So, you know that levels can be degenerate. Okay? And something you know, but you will say that you don't know, is that in general, so degeneracy is related to some symmetry in the Hamiltonian. Do you know this? No? So why, for instance, some levels are degenerate and some levels are not degenerate? So the hydrogen atom, okay? You take P levels, are they degenerate or not?
There.
Huh?
There.
There, right? So why there is some degeneracy?
Because for 1L we have different.
No, right. No, you're right. But is this just by chance or?
Symmetry of
The fact that there are degeneracy is related to the symmetry of the Hamiltonian. If you, for instance, if you break the symmetry, then probably these levels will not be necessarily, not this one, but in general, they will not be degenerate anymore. Hmm?
Yes.
We will come back to this, don't worry. But there are cases in which, when lambda is equal to 0, there is a degeneracy. Then you switch on lambda, V, and then the symmetry is broken. And so something which was degenerate, it becomes non-degenerate. Question. This is a big change, because you went from something which was double degenerate to two levels which are single degenerate. Do you see any continuity in this connection? No. So, I completely lost you, right? Huh? Good. Let's forget about this, okay? So, is the problem clear?
Yes.
Can we think about it in the free electron model, because we
No.
worked on that?
No.
Okay.
What are you working on? You are studying, not working.
Okay. Like this.
What do you do with the free electron model?
We just find the perturbation and split the energy levels.
Okay, so you know how to split, find the perturbation for a complicated system, and you don't know how to find it for a simple system, right? That's very interesting.
No, because then we can understand what the continuity means. This is my imagination.
Okay, so what is the free electron model? It's very interesting. So you know, you get confused with one electron and you can solve the problem with many electrons, right? That's brilliant. Okay, so let's consider the free electron model. Tell me, what do you know about the free electron model?
We know the shape of the band structure where it is.
Okay, very good. Okay, so first of all, you know that the free electron model is just, you have to solve a single particle wave function, and then you just use Fermi statistics. Okay, huh? Right? Are you happy about the free electron model? Okay. Now, tell me about the free electron model. Then you know that so what is the quantum number that you use to label the state?
Okay.
Okay.
Momentum.
Momentum. Very good. Now, just consider any whatever, so does not matter. Now, tell me, in the states that you write down, is there any degeneracy or not?
Yes.
And what is the degeneracy? This is a TV set, okay, radio, I don't know.
This is the Brillouin zone.
This is not the Brillouin zone. I never saw a Brillouin zone. So if I go to my son and say, look here, he will not tell me this is a Brillouin zone. He will tell me that you're crazy. So this will be reaction, okay? So, tell me.
There are two degeneracies. One degeneracy is k minus k.
Very good. So let's stop here. There is a degeneracy k minus k. Do you know why there is a degeneracy k minus k?
Because of the symmetry of Hamiltonian.
Yeah.
Okay, so you know, this is exactly the words that I used 2 minutes ago, and you said that you did not know. Okay? Now, think seriously. So this is an exercise for you. Just think, what is the symmetry of the Hamiltonian?
X minus x.
It's think. Okay? So, exercise. With the free electron model, you have degeneracy, then you have to find a perturbation which breaks the degeneracy k minus k. This is a difficult problem, but, okay? Not solve the problem, but just to see if you can find. This is a very difficult question for you. Now, what do you know about perturbation and band structure? Say it.
It breaks the symmetry.
No, say it. You start from free electrons.
Okay.
Free electrons, what happens? The wave functions are?
Plane wave.
Plane waves, okay? Now, then you put a tiny potential, periodic potential. What happened on the
Plane waves interact with potentials and their shape is...
No. Plane waves do not interact with potentials. So I know what you want to say, but this is not, a plane wave does not interact with a potential, because a plane wave is a description of the system when there is no potential, okay?
Potential changes the band structure.
This is a better way to say it. So if you have a potential, it modifies the plane, the wave functions, okay? So do you remember where it modifies strongly and where it modifies?
The point of degeneracy. At the edge of Brillouin zone, if we're talking about...
So there are regions in which the band structure is not modified, or very slightly. Then you go to the edge of the Brillouin zone, there is a strong modification. Okay? So you know everything. Okay? Now what you have to do is just to get the abstract picture. So you should apply this to any problem. So it's not that your life will be just free electrons. So some of you will do this, some of you will do that, and then you have to get the general picture and apply to any problem. Okay? So in this case that you consider, you have a situation in which if you are far away from the edge, then there is a modification in the... So the picture that you remember is this following. So this is the free band, okay? Then you will start seeing something like this. Okay, right? So the closer you go to the edge, then the larger the deviation occurs. So you see, here there will be a deviation. But it's tiny, tiny, tiny. So if I just plot, you don't see it. So you go closer here, when you see that it is modified. Okay? Now, what happened here? So here what happened is that these are the bands. There is a modification which goes like this, right? All this you know. So in principle, I can just skip the lecture today. Because you know everything. Now, the effort that you have to make is that all the concepts that are here should be put in any problem you want to study. Okay? So, what I'm going to do today is not giving you new concepts. Okay? I would like to revise the general approach so that you can apply the same idea to this problem, to a spin in a magnetic field, to whatever, okay? An oscillator, an anharmonic oscillator, these are different problems, but the approach is, there are some key concepts which are all the same, okay?
What I was trying to ask is, you asked us about the continuity, and when I see this, I think it is continuous, but
very
it's
good.
also not continuous.
So you see, there is this point in which there is no continuity. Because you go from one double degeneracy to two solutions and a gap. Here, there is a kind of continuity, because you can say that this solution, so this energy was the former and it was there. Okay? So the solution that you use here was different. You just use a two-state, effective two-state problem, so that, okay? Now, I would like to start with a simple problem that you know, but probably since it's simple, then it will become, you don't like it, okay? So I would like to start with a simple problem that I can solve exactly, but where I would like to do perturbation theory. Okay? Now, I consider a two-state Hamiltonian. It is not really, it's not important to specify the why it's two-state, okay? I just consider an Hamiltonian which is a 2x2 matrix. And the Hamiltonian H0 plus lambda V in matrix form is this form. It has this H01, H02 plus lambda V11, lambda V21, lambda V12 plus lambda V22. Okay? This is my Hamiltonian. I just take, so it's two-dimensional, just take two bases which are labeled by 1 and 2. And now, what are the unperturbed eigenvalues? So the unperturbed eigenvalues are E01 and E02, right? And the eigenfunction, we call it 501 and 502. Okay? So these are the solution when lambda is 0. Now, I would like to study the eigenvalue for any value of lambda. In this, okay. So this is simple, it's just the quadratic equation, okay, to finding the eigenvalues. So you solve it, I just write down the solution, otherwise, because I would like to discuss the I just put plus minus for reason that you will see in a second. So the solution is symbol for the eigenvalues, and it's just E0 2 plus lambda v2 2 times E0 1 plus lambda v1 1 plus minus, and now I write it in this way, okay? It's in a way which is useful for our discussion. Okay, times 1 plus lambda square okay.
No square there down there.
No. Ah, here, yes. Sorry. This one. Right. Okay. So it is written in such a clumsy way for the following reason. So this is the exact solution, okay? Now you see that if you put lambda equals 0, this goes to 1, okay? Yeah, sorry, I just did sorry. So, I just tried it. So this is plus, and this is minus, okay? Otherwise it was going to be when dimension is incorrect. Okay? So if I put lambda to 0, then I have one solution with a plus will be E02, and the other solution is E01. Okay? Which are the solutions. Okay? Now, if I want to know the approximate solution when lambda is small, what should I do? Huh?
When lambda is what?
Small. So when lambda is 0, E plus minus, it's either E1 or E2. Okay? Now I would like to know what is the what should I do when lambda is small? What does it mean small? We'll discuss in a second. Okay?
First of all, we have to take care of the square root.
How do we take care?
Yes, he said like Taylor expanded.
Who said so? I did not know. Okay, but this was.
All
Did you
credits,
say?
all credits to him.
Okay, very good. Say it.
Nice.
You have to expand. Okay? So here, this is simple. Here you get terms which are zero order in lambda and first order. That's it. Okay? Then you have to expand this in power, and then you decide where to stop. Okay? Now, first question. From here you get linear corrections. Okay? Corrections which are order of lambda, which are linear in lambda. Okay? Now, from here you get correction which are linear, quadratic, cubic, whatever in lambda. Tell me.
Quadratic and cubic also.
So, you get quadratic and cubic or everything. So, this is a good answer in the sense, the first correction that comes out from here is the quadratic term. Okay? Then there will be cubic, quartic, whatever. Is it okay or not?
Yeah.
Is it okay? So, should I come there? No.
Why shouldn't it be okay?
No, I don't know. Is it okay for you? Is it okay? I'm not sure that it's okay. Is it okay? Okay, since it is okay, then you tell me what is the solution. So, let's do it for E plus, okay? E plus is what? The zero order is? No? Come on, don't write for the moment, just think.
E plus has to be
So the zero order, this is a simple question,
2. E02, it's the zero order.
okay?
R plus.
So the zero order of E plus is when I put lambda to 0, okay? And if I put lambda to 0, I will get, this is 1, and here I will get E02 half plus E02 half.
Yeah.
Now, what is the linear term?
There will be no linear terms coming from the square root.
Just a moment. Yes, there is no linear term coming from the square root because, so tell me, very good. So if I have something like 1 plus lambda square something, so this is what?
1 plus lambda square half.
This is 1 plus lambda square over 2, okay? And it's enough that I put lambda square here, so I just, if I want to stop at the square, then this I can put to 0. Okay? Now, so this, for the linear term I can put to 1, equal to 1, and then what is the correction to linear?
Lambda v2
E1 plus E2.
Okay, shut up now, all the rest, tell me, what is the linear correction?
B11 plus.
No, you shut up. What is the linear? what is the linear correction?
For lambda equal how much?
No, there is no how much. I have to do a Taylor expansion. So out of this, if I put this equal to 1, what is the linear term which remains here? Huh?
Lambda v.
Hmm? Where is lambda b0? Where is lambda b0?
I'm asking if lambda is equal to 0. Is lambda equal to 0?
If lambda is equal to 0, this is the solution. Then we said that there is a term which is proportional to lambda. Okay, what should I put here?
V2 plus V11.
V?
2 plus V11.
Okay, let's do it. Okay? So, since we are putting here 1, this is E02 plus lambda V22 plus A01 plus lambda V11 minus, plus E02 plus lambda V22 minus E01 minus lambda V11. And this should be divided by 2. Okay? Then, tell me, what should I simplify? Eh? I'm not so sure. Talk loudly, please. I don't hear.
We will simplify V11 and E10.
So, this is plus and this is minus. So,
Cancel.
they cancel. They cancel. So, remains here what? Lambda
V22.
V22. Okay? Now, this is the linear, okay? Then you have to determine the quadratic. So this is just a function of lambda, okay? Once you have a function of lambda, do you know how to do the Taylor expansion? Now, this is a clear question. You should tell me, yes, I know, no, I don't. The question is clear. So tell me, do you know how to do a Taylor expansion?
Yes.
Huh?
Yes.
Okay. So tomorrow you just do it, and I want to, you also do it, okay? And I want to see on the notes, okay, the Taylor expansion of this function up to order lambda squared. Okay? So we just meet at 5 to 11. So in 5 minutes I really would like to check the the Taylor expansion of everybody. Huh? Now you do it, and then you find plus lambda square V12 squared E02 minus and then there is, the rest. Huh? Now, something I really would like to know is the following. So according to your intuition, when the perturbation expansion is a good approach?
Or it's non-degenerate.
No, let's assume it's non-degenerate. Okay?
When every consecutive term is even smaller and smaller.
Okay? So if I'm doing perturbation expansion, I'm assuming that this term will be just a small correction to this one. This term will be a small correction to the previous one. Okay? Now, do you see that, for instance, let's consider the first term here. Okay? Can you find out lambdas such that perturbation, the first order correction is there is something which lost something? Okay. So what does it mean small?
The ratio of this term to that term is smaller than 1.
Right. So this means that lambda should be much smaller than E02 divided by V22. Okay? So I have to ask if this is much smaller than this. Okay? Now, let's analyze this term. Again, you have to decide that this term here is much smaller than the previous one. Okay? There is an interesting term which appears here. That is the ratio. So let me say, let's consider for simplicity the case in which the diagonal terms are 0. Okay? This to simplify the discussion, it's not really important, okay? So now I would like to discuss the limiting case where V11 equal to V22 equals 0. Okay? Now, E plus is just equal to E02 plus lambda square V12 square divided by okay? If you do the same for E minus, you will get I think, yes. Okay? You just do it and you find Tell me, when lambda is equal to 0, what is the gap between the two eigenvalues, the energy difference? the energy difference is just E0 minus, okay? Now, I really would like to take the difference, okay? So I would like to compute E plus minus E minus. This is equal to E02 minus E01 plus twice lambda squared okay? Huh? So I just take this and I get this is equal E02 minus E01 plus twice lambda squared mu squared divided by okay? Sorry. Okay? Now, this is the gap, the energy gap, when lambda is different from 0. This is the energy gap when lambda is 0. Now, when perturbation theory is good, when this correction is much smaller than 1. So you see that what you have to, what is the important ratio to compare are the matrix element, the off-diagonal matrix element, with the gap. When the gap is much smaller than this, when this is much larger than 1, probably you have to go to lambda very, very small, such that this correction is small, much smaller than 1. Okay? So, something which is essential in perturbation theory is the fact that you have to always define dimensionless quantities in order to decide if a perturbation is small or is large. Okay? But just saying small, large does not mean anything. Now, just think to the example of free electrons. Okay? I would like to know what happens if E02 minus is equal to, sorry, E02 is equal to E01. Huh?
Then this expression is not correct.
So when E02 is equal to 0,1, perturbation theory that never works. Okay, because this will be always infinite. But is this expression correct or not? So for the moment, let's consider again the case in which this is 0, okay?
Then no.
Be careful, because there is a 0 here. So I just rewrite. Huh? I just rewrite. Is this clear below? Yes. So I want to rewrite again this expression when V1 and V22 are 0, okay? This is E plus minus equal we are just saying I want, okay, I just consider E02 plus E012 plus minus okay? Now, he said, look, it does not work because this is 0 and it blows down, up. But be careful. So this goes to 0. This is not well defined because it's at 0 times infinite. And the reason why is that in solving this equation, we just pull out of the square root this term, which is 0. So we multiply by 0. So we cannot use this solution. Let's try to see what is the solution. Okay? So I just rewrite the matrix, which was E0, A0, lambda V12, lambda or. Okay? This was the matrix. Now, the eigenvalues are plus minus are equal to E0. You can try to solve it, okay? Plus minus, what is lambda V12 modulus. This is the solution. So you see that the exact solution is okay. If I try to extract from perturbation theory, I get something wrong. This is an example in which this is a point in which the H0 was double degenerate. Okay? As long as the zero order problem was non-degenerate, I could do this. But then, if I have some degeneracy, I have to do something more careful. Now, this was one example. Let's do the theory. Huh?
Sorry, I have a question.
Yes.
In the case when the perturbation had only these off-diagonal terms,
Yes.
and the two states were non-degenerate, the quadratic term gave us the shift in energies.
Yes.
But in the degenerate case, it was the linear term that was giving us the split.
Now,
Why
what
is-
happened is the following. This was an extra complication.
Yeah.
If you put a perturbation, then it can just simply means that by the linear term, then you have a splitting of degeneracy.
Yeah.
This is okay, but it may be that the quadratic term blows up.
Yes.
Okay?
Now in this case, actually,
So in this,
there was no quadratic term in the case that we saw.
which one?
When the matrix was E plus, I mean on the next,
Yeah.
it was lambda V1, whatever. Yeah. And the energies was E plus minus, is equal to E0 plus minus lambda
Yes.
V. And there was no other correction.
I know, because this was the exact solution.
Yeah.
So the reason why I wrote down this is that the exact solution, you see that the exact solution was related to something lambda V12.
Yeah.
Okay. So you see, this is the modulus. It means that this is not Taylor expansion.
Yeah.
Okay. So this was the exact solution. And the only thing I'm saying is that the exact solution is perfectly well defined and is proportional to the modulus of lambda, but this can never be obtained by some perturbation expansion.
Ah, okay, I understand.
This is the only thing I want to tell you. So if you try to do a perturbation expansion, you get something wrong. Okay? So, the second, so on the first page you do the Taylor expansion. And the Taylor expansion should be in one page. When I was a little kid, in the dinosaur area, then, so I remember that in the primary school, we got marks, right? So, I don't know, for any. And then there was one extra, so in Italy the system it goes from 0 to 10, okay? And you pass when at least you have 6. So the teachers also always gave one extra point if you write down with a nice calligraphy, okay? So whenever I was unable to do a solution, then I just made the wrong thing, but written in a very nice way. Okay, so I will not take points for the. So write in a clear way. So don't produce things that I don't understand. Just write the initial equation, the initial formula for the eigenvalues. Then you write first order, second order. Okay. Now, I forgot, I wanted to give you a second exercise. I forgot, so. Let me think. Yes. Now, take this. Take this Hamiltonian. Okay? You can write lambda, lambda, okay? Now, so you have a graph, so you have to prepare a plot, lambda in units of is 0, for example. Okay? No, sorry, lambda is, we take it this way, so it's dimensionless. Huh? Lambda is dimensionless. So I want to see the plotting here, the two eigenvalues when lambda is equal to 0. So H0 is there is a minus sign here, minus plus. Okay? Okay? This is H0, this is H. You should plot
minus lambda v.
No, it should be a median, so this is okay. I will have to find, yeah. Okay. So I want a decent plot, of the eigenvalues of h and h0 as a function of lambda, okay? And the decent plot of the eigenvalue as a function of v divided by, E0 okay? Huh? Is the question clear? So tomorrow you should not say I did not understand. Okay? So you have to find the eigenvalues of this, the eigenvalues of this, and then you choose the right units, the units that you like. Okay? And then you have to produce two plots, one as a function of lambda and one as a function of E0 over B. Okay? Good. So now in the last 10 minutes we do the perturbation theory. So, as I said before, we know the solution of this problem. And we want to find the solution of this problem. Okay? Now, what we do is just assume that we can write down a Taylor, as we did for the two-state example. We assume that, so this time-independent, non-degenerate, we assume that we can write a Taylor expansion for both the states and the eigenvalues. Okay? So we just say E n of lambda is just equal to E0 n plus lambda E1 n plus lambda squared E2 n, whatever. And the same way we can write phi n is equal to phi 0 of n plus lambda phi 1 of n plus lambda squared. Okay? Now notice that the fact that I can write down a Taylor expansion is related to the fact that there is some continuity. The index n is the one of the unperturbed state. Okay? So the spectrum is slightly modified, but you cannot have crossing or wild things. So what you do is just take this and you put it here. And then you will get a polynomial in lambda on the right side, on the left side, and the polynomial in lambda on the right side. And then you start equating, because so term by term they should be equal. Because the identity should, so the equality should hold for any lambda. Okay? So you just write the thing here, and then you put gathering together things which are of the same order in lambda. So you see that lambda equals 0. The only term which survives is just H0 phi 0 equal to E0 phi 0. Okay? So let's see. Oh, okay, I just write it so that you see. So you have H0 plus lambda B phi 0 of n plus lambda phi 1 of n equal to E0 of n plus lambda E1 of n plus, which multiplies phi 0 of n plus lambda phi 1 of n. Okay? So let's see the zero order. The zero order is when H0 multiplies phi 0 equal E0 multiplies phi 0. Okay? Which is satisfied by construction. So let's see the first order. From here you get this multiplying this. So you have H0 phi 1 of n plus V phi of n equal to
E0 E1
okay? So if we group things, this is just H0 minus E0 n, which multiplies phi 1 of n plus V minus E okay? Good. Is this clear?
Yeah.
Okay. So we have to find the solution. But you see, the idea is that you have to find ways in which you determine phi 1 and E1 starting from the solution phi 0 and E0. So you just multiply this equation by phi 0 n. If you multiply this by phi 0 n, then this becomes 0. Okay? Because H0 applied to phi 0 n is just E0 n, so you get something minus the same is 0. So you get here phi 0 of n V phi 0 of n equal, or sorry, minus, okay, phi 0, which is 1. So you get this. So you see that you found the first correction. E1 is just this. Okay? Then, now you want to also find the correction to phi 1, to the eigenstate. Okay, you just multiply by Not the same n, but a different n, m. Okay? This you do it yourself. Okay? So I can give you the solution, and tomorrow we do it. Since tomorrow we do it again, it's better that you try it. So you will find that phi n is just equal to phi 0 of n plus, and then you get some m different from n So this is the first order correction. Now you see that now this will not be only n, but there will be overlaps with the other states, because this is not anymore an eigenstate. And also again here you see that it is important that there are no degeneracy, otherwise this will blow to infinity. So we continue tomorrow. Now,